So in this question, we're going to be dealing with two conversion lenses. It's going to be f1 and f2, and light's going to pass through both of these lenses to create an image, which is right here. f1 has a focal length of 10 centimeters, while f2 has a focal length of 20 centimeters. The distance between these two convergent lenses is 50 centimeters exactly and is represented by D right here. Additional information is given to us about the image that is formed by light passing through both the lenses, which is located 31 centimeters from the first lens. So from f1 to right here is 31 centimeters and is represented by the X right here. By using the information I had just given you, we should be able to answer these four questions. A. At what value of P should the object be positioned to the left of the first lens? B. What is the magnification of the final image? C. Is the final image upright or inverted? And D. Is the final image real or virtue? We've done a lab like this in our physics lab, so hopefully this will be all review for us. So now we're going to be answering question A, which was at what value of P should the object be positioned to the left of the first lens. And this is going to be done by first figuring out the image distance to the second convex lens, which is represented by Q2. And this is going to be simple math. It's just going to be subtracting D minus X, which was the distance between both the converging lenses and the distance of the image that is formed. And we're going to get 50 minus 31, which would equal negative 19 due to the negative sign right here. We need to keep in mind that it is negative 19 because that may help us answer question C and D later on. So we are also given focal length of the second convex in the original equation, which was given to us as 20 centimeters right here. Using the lens equation we use often in class, 1 over f2 equals 1 over p2 plus 1 over q2, we're going to be able to derive this equation in order to get P2, which would be the object distance to the second lens. By doing that, we're going to get 1 over P2 equals 1 over F2 minus 1 over Q2. And after we have the equation, it's just going to be plug and chug. It will be 1 over 20 centimeters plus 1 over 19 centimeters. And after doing the math, you'll get P2 equals 9.74 centimeters. So after figuring the object distance to the second lens, which ended up being 9.74 centimeters, we were able to find our image distance to the first lens, which is done by very simple math. It's going to be the distance between both the convergent lenses, which is 50 centimeters minus what we just found earlier, which was 9.74 centimeters. After doing the math, we'll get 40.26 centimeters. As given earlier, the focal length for the first lens is 10 centimeters. So by using the information we've just gathered, we were able to first derive our lens equation, which was the same up here as over here. And we'll be able to derive it to Q1 minus F1 over F1 times Q1. And by plugging in the numbers that we found earlier, we'll be able to solve where the object needs to be placed to the left side of the first convex lens. So using this equation right here and with the information we've already given, we've already solved for Q1 and F1. F1 is the focal length of the first length, which was given, and F1 was what we solved right here for 40.26 centimeters. And by using those two numbers, we're going to plug it into this equation, which would end up being 10 times 40.26 over 40.26 minus 10. And you'll get 13.3 centimeters. So the final answer for A will be 13.3 centimeters to the left of the first convex lens. So the question we just answered before for A basically did all the math that we need in order to answer these last questions, B, C, and D. So the second question is asking us what is the magnification of the final image, and that's going to be done by using the magnification equation, which is fairly simple. So we're going to find the magnification of the first lens, and by doing that we use M equals negative Q1 over P1, and we're just going to plug in Q1 and P1 that we solved from the last question. So we're going to be using negative 40.26 centimeters over 13.3 centimeters, and by doing the math, we're going to get negative 3.03. And we got 40.26 and 13.3 just by using these numbers right here, 40.26 and 13.3. So no additional math is needed to solve for this question instead of just besides plugging in the equation. We're going to do the same exact thing for the second lens. We're going to find Q2 and P2 instead, which was negative 19 centimeters over 9.74, but because there's a negative 19 centimeters and a negative sign here, it's going to change to positive 1.95. And those numbers were right here and right here. So like I said before, no additional math needs to be done. After finding both of those numbers, we're going to find the total magnification of the final image, which is done by just multiplying negative 3.03 by 1.95. And after doing that, your answer will be negative 5.91. So the last two questions are fairly simple. You're just basically looking at the sign on the number, either if it's positive or negative. So for the first of the two, it's going to be what is the final image upright and inverted, and that's easily done by just looking at the magnification. So it's right here. It's going to be negative 5.91, and since it's negative, the image is considered inverted. For the second question of the two, is the final image real or virtual, and that's by looking at the image distance. And if we can go back, we remember the image distance being negative 19 exactly, and we can actually go back and look at that right now. The image distance is negative 19 centimeters, and from what we know, when a final image distance is negative, the image is a virtual image. So that is that's all. Thanks.